Hey everyone, let's jump right into this explainer and set the stage for mastering the mechanics of injection molding. Whether you realize it or not, the device you're watching this on, the car you drive, and the chair you're sitting in were all made possible by the incredible engineering behind plastic injection molding. Today, we're going to explore exactly how to set up the technological processes, the equipment, and the molds required to process injection molded products from start to finish.
Think about it for a second. How exactly do we perfectly mass-produce millions of identical plastic parts in just a matter of seconds? We're talking about extremely high stakes and pinpoint precision in modern manufacturing here. One tiny flaw in your initial setup, and you're suddenly looking at thousands of ruined parts.
Here's our roadmap for today. We'll quickly cover the anatomy of an injection mold, the four-stage molding cycle, perfecting flow and cooling, advanced rapid tooling, gas and water assistance, and finally optimizing with simulation. Let's get into it.
Part 1. Anatomy of an injection mold.
So, the absolutely crucial first step is understanding what an injection mold actually is, because it is definitely not just a hollow chunk of metal. An injection mold is a highly engineered, deeply complex piece of equipment. It uses fixed and moving plates to shape molten plastic. And here's the kicker. It has to mathematically account for exactly how much that specific plastic is going to shrink as it cools down. If you don't calculate for shrinkage in your initial setup, your final product is totally useless. You can really see the sheer mechanical bulk of a classic three-plate mold when it's closed up. Notice the heavy-duty guide pins, the support pillars, the clamping plates. This entire setup has to withstand massive amounts of pressure. We're talking thousands of tons sometimes, when that molten plastic is forced inside. Then, when the process finishes, the mold opens. The fixed cavity plate, which gives the product its outer shape, and the moving core plate, which forms the inside, pull apart. And that separation ultimately reveals the newly formed product, totally ready to be pushed out.
Moving to Section 2, the four-stage molding cycle.
The real manufacturing magic happens in this beautifully precise four-step sequence. First up is clamping, where the two halves of the mold lock together under immense force. Second is injection, where molten plastic is shot right into the cavity. Third is cooling, where the plastic solidifies. And fourth is ejection, where the mold opens and pins physically push the part out. What's completely mind-blowing is that this entire cycle can take anywhere from a couple of minutes down to a lightning-fast 2 seconds.
All right, Section 3, perfecting flow and cooling.
Now, before the plastic even reaches the mold cavity, it travels through a runner system. And this brings us to a huge setup rule, the gate. The gate is basically the doorway into the mold cavity, and it absolutely must have the smallest cross-section in the entire flow path. Why? Because it controls the shear rate and ensures a perfectly balanced flow. A properly designed runner system guarantees that if you have a mold with, say, multiple cavities, they all fill at the exact same time. That's how you get uniform quality across every single part.
But here's a wild stat for you. Filling the mold is really only half the battle. Remember that cooling stage we just mentioned? It consumes more than 50% of the total cycle time. Over half. So if you want to speed up production and save a ton of energy, setting up an incredibly efficient cooling system is absolutely critical.
To pull that off, engineers machine these strategically placed cooling channels right into the mold plates. By running coolant, like water, at around 19 degrees Celsius through these U-shaped channels, they maximize thermal dissipation. This rapid, highly controlled cooling is what permanently locks in the final shape and stops the plastic from warping.
Next up, Section 4, advanced molds and rapid tooling. Historically, getting a mold set up meant using hard tooling, which basically means machining solid blocks of steel. It's incredibly durable for high-volume runs, sure, but it takes months and costs tens of thousands of dollars. But today, we have soft tooling. Using 3D printing technologies like fused filament fabrication or stereolithography, engineers can print mold inserts out of thermoplastics or epoxies in just a few hours. It's a total game changer for rapid prototyping and low-volume, agile manufacturing.
We're actually seeing hybrid setups in action all the time now. Like for cosmetic compacts, engineers will use a standard traditional metal mold base, but they'll machine custom pockets into it. Those pockets perfectly hold these rapidly 3D printed tool inserts. It's brilliant because it allows designers to test part performance and surface finish without committing the massive time and money required to cut a full steel mold.
Section 5. Gas and water assistance.
Now what if you're trying to set up a mold to make something thick, curved, and hollow, like a heavy-duty handle? You wouldn't want it solid. For that, we use a brilliantly simple technique called the short shot process, aided by gas or water. In a normal setup, you'd fill the mold 100% full of plastic. But in a short shot, the injected melt volume is intentionally way less than the total cavity volume.
Here's how that specific setup works in practice. Step 1, you inject that short shot of melted plastic. Step 2, you blast high-pressure gas, or sometimes water, directly into the center of that molten plastic. The gas forces the plastic outward, pressing it super tightly against the walls of the mold. Step 3, the part cools and pops out. The result? A perfectly hollow part with amazing surface quality, leaving 10 to 30% empty space inside. It saves massive amounts of material, cuts down the weight, and completely prevents those ugly sink marks you get on thick plastic.
Finally, Section 6, Optimizing with Simulation. Look, before anyone even thinks about cutting a block of steel or 3D printing any resin, we have to verify the whole setup digitally using computer-aided engineering, or CAE. By simulating the exact flow of the plastic, calculating the precise clamping force, and mapping the cooling rates, engineers can spot total disasters before they ever happen in the real world. CAE prevents warping where the part bends, porosity where bubbles form, and weak weld lines where plastic flows crash into each other. It saves an unbelievable amount of time and money.
And today's cutting-edge setups, they take this way, way further. We aren't just simulating anymore, we're optimizing. Modern software automatically generates parametric mold geometries and runs incredibly deep thermomechanical analysis. Some systems are literally applying artificial neural networks, yet AI, to train surrogate models that instantly find the absolute best setup. This minimizes cycle time and drastically cuts down energy use, pushing the entire industry toward a much greener, more sustainable future.
So let's tie this whole explainer together. Whether we're talking about the heavy steel plates or the mold anatomy, balancing the runner gates, utilizing 3D printed soft tooling, injecting high-pressure gas, or running advanced AI simulations, every single one of these steps serves one absolutely critical engineering objective: setting up the technological processes, equipment, and molds to process injection molded products. Mastering this setup is literally what turns molten resin into the modern world around us.
Which leaves us with this final thought to chew on. We've seen how digital tools can predict and perfect a physical mold before a single piece of metal is ever cut. As our simulations and 3D printing technologies continue to evolve side by side, what impossible shapes will we be able to manufacture tomorrow? Thanks for joining me on this explainer. I really hope this sparked your curiosity about the incredible engineering behind the everyday objects we all take for granted.